2 deals with linear motion or straight line motion. So for this chapter, we're going to limit ourselves to an object that's either moving horizontally or perhaps traveling vertically, straight up or straight down. Now, position is a vector quantity that tells us where something is. Vector means it's going to have size or magnitude and direction. Usually if we're going to describe a position vector, you can think in terms of a number line. Let's look at just a number line. These will have units. Our SI unit for position is a meter. So perhaps we've got this marked in meters. If something is here, then its position would be 2 meters. You could say 2 meters to the right, but a lot of times just indicating that it's positive indicates it's right. With linear motion, we can use positive and negative for direction. If something was located here, that would be a position of -1 meter or 1 meter left. Notice if we say that it's left, I don't put the negative. We don't want a double negative like in English. But a position vector just tells where the object is relative to some point of reference that we usually call the origin. Displacement is another vector quantity. It is also a vector. It represents a change in position. It will be a vector. The SI unit is still the meter. The symbol for a displacement is a delta x. Anytime you see this triangle, that's a Greek letter delta, and it means a change. We usually write it x2 minus x1. Some books might use final minus initial, but a displacement is simply a change in position. For example, here's 0, x1 is 45 meters, x2 is way down here, that is 215 meters. If I said, what is the car's displacement? Here's a little car. I don't draw good cars, so we'll look at a car. It was here at some point. Later on, at a different time, it was here. Notice if I draw the arrow from where it was to where it ended up, you can see the displacement vector. It's a positive displacement because it moved to the right. That's going to come out to be 170 meters. So displacement's a pretty easy concept. And it's very closely related to the idea of an average velocity. Velocity, also a vector. The SI unit is meters per second. To represent average velocity, we use a V for velocity. A line over a variable, that's a symbol from statistics. It means the mean value or the average value. So when I put a line over this like that, that's telling me I want the average velocity. And it is simply equal to the change in position over the time interval. Sometimes you'll see an X to indicate that this was a velocity in the X direction. This is a horizontal problem. There aren't going to be any Y's in it. In this case, let's suppose that at this particular location, T1 was 5 seconds. And here at T2, somebody checked their clock and it said 10 seconds. So it's simply displacement divided by the time. We've already calculated the displacement, the 215 minus the 45. That was 170 meters. The time interval, T2 minus T1 is 5 seconds. 170 meters divided by 5 seconds is 34 meters per second. That's the average velocity. And that's really important to remember. It's an average. We don't actually know how fast it's going at any particular time. It could have been going very slowly right here. It could have actually started from rest. It might be going very, very quickly, much higher than 34 meters per second. That's just the average. Easy way to think about it. Suppose you drove from here to Bryan. Took you 2 hours exactly, just because that's an easy number. I don't even know how far it is to Bryan, but let's say it's 120 miles. If you drove 120 miles in 2 hours, you would had an average speed of 60 miles per hour. That was my distance, that was my time. It doesn't tell you how fast you drove the whole trip you went to Bryan. You may have stopped in Madisonville and gone to Buc-ee's, and all kinds of things may have happened. It just tells you on average, okay? We could have a similar problem. Here's our 0 on our number line. And we have somebody here starting at 1,600 meters at time t equals 0. And here's my little person. And they take off running. They cross the 0 marker at exactly 300.0 seconds. If I said, what's the average velocity? Change in x, change in time, or x2 minus x1, t2 minus t1. Well, the final position in this case, this would be x1. He's starting here. This would be x2. So we get 0 minus 1,600 meters. And we get T1 was 0, T2 is 300 seconds. So 300.0 seconds minus 0.0, that works out to be about a negative 5.3 meters per second. What you'll notice here is this time our displacement was a negative value. If our displacement is a negative value, then we must have moved in a negative direction. It makes sense that that gives us a negative velocity. Now, I want to emphasize that there is an important difference between velocity and speed. They seem very, very similar, and in everyday language we'll use those words interchangeably, but they're really not the same thing. Let's consider a swimmer. So, we have a swimmer, and the swimmer swims 50.0 meters to the other side of the pool. In 24.0 seconds. She immediately turns around and swims back taking twice as long. Well, what's twice as long? She took 48 seconds. I want us to find really 6 things. I want us to find her average speed and velocity for the first lap. I want to find her average speed and velocity for the second lap. And I want to find her average speed and velocity for the round trip. Let's start with the first lap. We haven't even talked about speed yet, but speed is a scalar quantity. Speed tells us how fast, and you can remember it's scalar because speed and scalar both start with S, but it doesn't have any dependence on direction. Speed is simply distance over time. So in this case, let's draw a picture of our pool down here. There's our 50-meter finish line. This is 0. They don't tell us where to begin, but it makes sense to say, I'm going to let my swimmer start down here swimming. Here she is, arms in the water, legs kicking. She's swimming. And finish here for the first lap. So, what distance did she swim? Well, she swam 50 meters. How long did it take her to swim 50 meters? It took 24.0 seconds. What was her speed? 2.08 meters per second. Makes perfect sense. There won't be much difference with her velocity. A lot of times with straight line motion, it's really similar. Her average velocity would be her displacement. Well, she went from 0 to 50, so 50 minus 0 meters. It took 24.0 seconds. I do have 3 significant digits here. And that comes out to be 2.08 meters per second also. The only difference between these two really right now is direction. This is in the positive direction. That might be to the right, it might be whatever we want to say. But the first lap, we don't see any difference at all between speed and velocity. Let's look at the second lap. For the second lap, she has to turn around. She's down at this end. And now she's going to swim back the other way. There she is swimming away. She's now traveling not in the positive direction, but in the negative direction. However, when we do her speed for the second lap, her distance is still 50 meters. Distance is not a vector. It's always positive. Distance is simply how far she went. She went a distance of 50 meters. It took 24 seconds. So her speed for the second lap, also 2.08 meters per second. Her velocity is going to change though. If we do our velocity formula, she starts here and she ends here. Her displacement is going to be 0 minus 50. The time interval is 4. I messed up the second lap. This won't be the same because she swam slowly. Let's go back. So for the second lap, her distance was 50 meters, but her time was 48 seconds. I forgot she swam slowly. So the second lap has a speed of 1.04 meters per second. Okay, that makes sense. She went twice as slow. Perfect. Now, her velocity divided by 48 seconds. And what we see is we end up with a negative displacement again. Her displacement, her change in position is in the negative direction. This gives me negative 1.04 meters per second. Again, the size of the speed and the size of the velocity, the magnitudes are exactly the same, but this is not a vector, so it's just a speed of 1.04 meters per second. This is a speed of 1.04 meters per second to the left or in the negative direction. All right, let's do the round trip. Now let's stop and think for just a minute. If the first lap was at 2 meters per second, roughly, and the second lap she had a speed of 1 meter per second, roughly, a lot of students, if I said, and I usually would ask a class, what do you think her average speed for the round trip is? They'll say, oh, about 1.5, halfway between 1 and 2. And at first that might seem right, but it's not going to actually be that close. Think about the round trip. The total distance for the round trip was 100 meters. The total time for the round trip was 24 seconds plus 48 seconds. That comes out to be 72 seconds. And it actually comes out to be about 1.39 meters per second. That's a little slower than we might have guessed if you tried to go right in the middle of 1.04 and 2.08. The reason is, if we stop and think, is she swam slowly for a much longer period of time. In other words, the second lap had a greater effect on the average speed than the first lap because it took twice as long. Now, here's the fun one. What's her average velocity? Well, here she is. She went all the way there, and she turned around and she went all the way back. She ended at 0. She started at 0. Her displacement was 0. The time was 72 seconds, but that really doesn't matter. Her average velocity was 0 meters per second. Makes perfect sense. She had a positive velocity for the first part of the trip. She had a negative velocity the second part. The average velocity came out to be 0. Anytime the displacement is 0, the average velocity is 0. Certainly, at any moment, she wasn't going 0. That's different. That's instantaneous velocity. We'll talk about that. For the first half, from here to here, she had a positive instantaneous velocity. When she's going back, she had a negative instantaneous velocity. But for our round trip, the average velocity is 0. Anytime you start and stop at the same point, your displacement's 0. Displacement is simply a change in position. If your position didn't change, it doesn't matter. So if you go out and run laps, you could have a very quick average speed, but if you start and stop at the same point on a circular track, your average velocity will be 0. Now, there's two graphs we use a lot when we're in physics. One is a position time graph. The other is a velocity time graph. And I say we use it a lot. We use it a lot in the first chapters 2 and 3 when we're looking at motion. Let's look at position time graphs. Now, generally in physics, we consider time to be our independent variable, which means it goes on the x-axis or the horizontal, and other things tend to depend on time. Your position might depend on time, your velocity or acceleration might be a function of time. So we do position over here, time here. Now, this may seem odd because we define position as x for a horizontal problem, but that's okay. And this will be t. We generally are going to measure this in meters. And so let's just go 1, 2, 3, 4, 5. So let's suppose 10.0 meters, 20.0 meters, 30.0, 40.0, 50.0. This is x and it's in meters. Time, we're going to go with 1, 2, 3, 4, 5, 6. Here's our time, it's in seconds. Anytime you're doing a graph, it's really important not only to indicate what you're measuring, but what your units of measurement are. I need to know, are you measuring time in seconds, or are you measuring time in minutes or hours, or days, or years? Same thing for the distance, but I went with our standard SI units, meters and seconds. And suppose that we've got an object. I'm going to label that point 2, 8. And I'm going to label this point 6, 40. But the actual graph of the motion might look something like this. We don't know what's going on, but we know this point and we know this point. If I said, let's find the average velocity between those 2 points, we would say, well, the average velocity is the displacement over the time. Now look at that for a minute. That's the vertical change from here to here. That's what x is on this graph, over the horizontal change from here to here. That looks exactly like slope did in algebra. Slope is rise over run, or change in y over change in x. Well, our letters are different, but that's rise over run. So if I want to get an average velocity, it's just the slope. If I were to draw it, I wish I had my ruler right here, I don't see it. I would connect these points with a straight line, and I would just be finding the slope of that straight line. So on a position time graph, the average velocity is the slope between 2 points, the slope of a straight line segment. So the slope of this line is equal to the average velocity. So if you find the slope between 2 points on a position time graph, you're going to find the average velocity. And that brings us to the idea of instantaneous velocity. Let's think about what instantaneous velocity would look like. Well, it's really, really hard to actually have a time interval go to 0, but that's the definition. I'm going to try to not erase this picture because it's an interesting picture. But if I want to talk about instantaneous velocity, what I want to do is, instead of having a long period of time, I want to make that time period really, really short. So if I were to give you a definition for instantaneous velocity, the instantaneous velocity in the x direction is the limit as the time interval approaches 0 of the change in x over change in t. In other words, I want to make this time interval really, really small. And if we were in a calculus-based course, we'd understand that this is a derivative, but we're not. Hopefully, you're in a course where everybody's had pre-cal already, because we are going to do a lot of trig. I probably should have mentioned it sooner. If you don't have pre-cal, you haven't done trig, you're probably going to end up over your head, and you should take your pre-cal class first. All right, well, let's think about what happens. Suppose if I make the time interval a little bit shorter, instead of going all the way from 2 seconds to 6 seconds, what if I only went from 2 seconds to 4 seconds? Well, it's actually fairly straight in there, isn't it? Looks something like this. Let me make it a little more wiggly just for interest's sake. Make it just a little less straight there. There we go. That's less straight. If I go from here to here, notice when I connect those points, I get a different slope. I made that time interval smaller. What I want to do is make it so small that I get the tangent line. Let me draw a different picture now. Whoops. If I wanted to know the instantaneous speed at 4 seconds, I'd want to make a tiny short interval. So short, in fact, that the line would be tangent. So, if I want to find on a position time graph, if I'm interested in instantaneous velocity, then I'm interested in the slope of a tangent line. If I'm interested in average velocity, then I'm interested in the slope between these 2 points. Now, I'm not going to actually calculate that, but I want us to look at how we can make some interpretations. Let's see if we can figure out, I want us to, this is an example, I want us to find the sign. By sign, I mean positive or negative. I want to find the sign of the position and velocity vectors at each point that I'm going to label on this graph. So that's position. And remember, position can be positive or negative. And here's time. And here's my graph. Okay, we'll label some points. I'm going to label point A, point B, point C, point D, point E, point F. I have a lot of points. I'll tell you what, I'm going to write the word time under here. I'm going to make a little table over here. Tables are really useful for organizing information. So I'm going to put the point, and then I'm going to talk about the position, and I'm going to talk about the velocity. Here's our points, A, B, C, D, E, F. Well, let's look at the position at point A. We know that this end of the number line would be positive, this end would be negative. So we're starting off below this horizontal axis. So this is a negative position. But I want us to look at the slope. The instantaneous velocity is the slope of this line. This velocity points that direction. So that's a positive velocity. If we look at point B, it has a positive position. You know what, let's move E right here. There's E. B has a positive position, but it also still has, you can see this is a very steep slope, a positive velocity. Now, at point C, the position's clearly positive. It's up at the top here. But this, whoa, that's a horizontal line. That's a slope of 0. That makes sense because if this is a positive velocity going up, and this is going to be a negative velocity coming down, then right there where it changes direction from positive to negative, that's a 0 velocity. Notice point D, positive position, also looks to be at a flat place. I think that's 0 velocity. Point E is sitting on the horizontal axis. That means its position is not positive or negative. It has a position of 0. But what's the direction of its slope? That's a negative slope. That's a negative velocity. Point F has a negative position and a negative velocity. One of the things I want you to understand is it's entirely possible to have any combination of positive and negative positions, positive and negative velocities, and although we haven't talked about it yet, positive and negative accelerations. Okay, but if I have a position time graph, it's very easy to look and decide, is that a positive or negative position? And then to look at the points and decide, look at the slope. Positive slope means you have a positive velocity, you're moving in the positive direction. Here you can see they're going from a negative value up here to a positive value. That's a positive velocity. If the slope is 0, it means for that moment, you're not changing. Like here, it looks like he's just not changing his position. Well, if you're not changing your position, you're standing still. That's a 0 velocity. Here we can see he's clearly moving in the negative direction. Let's do one problem. Suppose we've got a cheetah, and that cheetah's position is given as a function. And it says that x is equal to 20.0 plus 5.00 t squared. And everything is in meters and seconds. I didn't put in the units because I don't want to gobble this up too much. This is 20 meters. This is 5 meters per second squared times the time squared. So everything's in meters per second. Let's find the displacement. I'll just write this in. And the average velocity between t equal 1.00 and 2.00 seconds. Well, let's find, this is a function of time. If I want when t equal 1 second, that's going to be 20.0 plus 5. I'm going to leave off the extra zeros times 1 squared. The time is 1. That's going to be 25 meters. We could call that x1, right? At 2 seconds, it's 20 plus 5 times 2 squared. Oh, that comes out to be 40 meters. Now, all of this is to 3 significant digits. I didn't write it here where I do my work, but that means my displacement, x2 minus x1, is going to be 40.0 minus 25.0, or 15.0 meters. That's pretty straightforward. Average velocity, change in position over change in time, 15.0 meters, 1.00 seconds. How did I get that? We went from 1 to 2 seconds. That's a time interval of 1 second. And I get an average velocity of 15.0 meters per second. So the displacement was 15 meters. The average velocity, 15 meters per second. Let's do a different problem with this same position function. Find the instantaneous velocity at t equal 1 by taking delta t to equal, 0.100 seconds. In other words, I'm going to let my time interval be 1/10 of a second. Not 1 second like I did a minute ago and I got 15 meters per second. I'm going to let it be 1/10 of a second. So, what was my position at 1? Well, it's 20 plus 5 times 1. It was 25.0 meters. But what would be my position 1.1 if I only go 1/10 of a second longer? I'm going to have 20 plus 5 times 1.1 squared 20 plus 5 times 1.1 squared, 26.05 meters. Now I know that's a few too many significant digits, but I don't want to round here, I want to round at the end. So my average velocity my final position was 26.05, my original was 25.0. My time interval was 1.1 second minus 1.0 seconds. So I end up with 1.05 meters over 0.10 seconds. When I divide that, I get 10.5 meters per second. Well, that tells me that's an estimate. It's not exact. I would need a little calculus to do it exactly, but it's pretty close. That at 1 second, he was going about 10.5 meters per second. We found, remember a minute ago, his average speed was 15 meters per second. Just shows that average velocity can be very different than an instantaneous. If I do the same thing for 2 seconds, I want to find the position at 2 seconds. I'm going to have to put a 2 squared here. 1 squared is 1, but 2 squared is 12. Remember, he ended up at 40 meters. That's the same result we got earlier. If I wait 1/10 of a second later to 2.1 seconds, okay, 20 plus 5, 2.1 squared, I get 42.05. That means the average velocity, 42.05 minus 40, that's my displacement. My time interval was 2.1 seconds minus 2.0 seconds. Okay, so I got 2.05 meters. And really I have 3 significant digits, so I'll keep them all. That's 20.5 meters per second. Obviously, our cheetah's velocity is changing quite a bit. At 1 second, it was going about 10.5 meters per second. At 2 seconds, it's going roughly 20.5 meters per second. We see how we got that average velocity of 15 meters per second. We have a changing speed. All right, if I have a change in velocity, I have an acceleration. Acceleration is any change in velocity. How can you change your velocity? Well, remember, velocity not only tells you how fast you're going, what your speed is, but also your direction. So the way you can change your velocity is you can speed up, you can slow down, or you can change direction. All of those are an acceleration because they're all a change in velocity. Everybody thinks of acceleration meaning speeding up, but it also could mean you're slowing down. It also could mean you're keeping the same speed and going around the curve. Speed up, slow down, change direction. Those are accelerations. Now, just like position tells us, just like velocity tells us how our position is changing, acceleration tells us how our velocity is changing. Say that again. Velocity tells us how our position is changing. I'm moving 15 kilometers per hour north. That tells you my position's changing 15 kilometers every hour towards the north. Acceleration tells us how our velocity is changing. The average acceleration in the x direction, and this could be in the y direction, but we're just working with horizontal now, is simply your change in velocity over the time interval. The average acceleration is the change in the velocity divided by the time, or v2 minus v1 over t2 minus t1. It is a vector. Acceleration definitely is a vector. The SI unit, which is our standard metric unit, is going to be meters per second divided by seconds. We can call that a meter per second. And we can talk about accelerations of things like miles per hour per second. But if we're using meters per second, we normally are going to write that as meters per second squared. So that's our SI unit for acceleration. There's some interesting things we need to understand. One is when velocity and acceleration point in the same direction. Another way of saying that is they have the same sign. If we're doing linear motion, they're either both in the positive direction or they're both in the negative. When they point in the same direction, speed increases. So if I'm driving 50 miles an hour to the east and my acceleration is towards the east, I'm going to gain speed. I'm going to speed up. When velocity and acceleration point in opposite directions, that means they have different signs or opposite signs. One is positive, one is negative. Speed decreases. If you're driving your car to the east, but your acceleration is to the west, you're going to slow down. It's the difference between stepping on the gas and stepping on the brake. If you're driving east and you step on your accelerator, your gas pedal, you accelerate to the east and you go faster. But if you're driving to the east and you step on your brake, your acceleration is actually to the west. You're moving east, but you're accelerating west, you're going to slow down. If you keep stepping on your brakes, you're eventually going to stop. Let's look at instantaneous acceleration. Instantaneous acceleration. Again, if we take that bar off the top, it's no longer an average. If I just want the acceleration, it's going to be the limit as the time interval goes to 0, as we make that time interval really, really short of the change in velocity over the change in time. Again, if we were on a calculus course, we would just say that the acceleration was dx dt, but we're not into derivatives yet. So we think of it as just being a limit Let's make that time really, really short, and that's going to be instantaneous. If I have a velocity function, in other words, this velocity is not a constant velocity, but it depends on time, and it is equal to 60 plus 0.500t squared. And again, everything's going to be in meters per second. So this is 60 meters per second. All the units are right. I just don't want to write the units because it kind of muddles up on the board. Let's find the average acceleration we want to find the average acceleration from t1, which is 1 second, to, I'll just say from t equal 1 second to t equal 3 seconds. I want to find the average acceleration from 1 to 3 seconds. Well, the velocity at 1 second is 60 plus 0.500 times 1 squared. I just plug that in. That's just going to be 60.5 meters per second. If I say, what's the velocity at 3 seconds? That's 60 plus 0.500 times 3 squared. That's 9, half a 9 is 4.5. It's going to be 64.5 meters per second. So I know how fast I'm going at 1 second. I know how fast I'm going at 3 seconds. So my average acceleration is just 64.5 minus 60.5 meters per second. That's V2, this is V1, final minus initial. That was the time interval of 3 seconds minus 1 second. And it comes out to be 4.0 meters per second divided by 2.00 seconds. I'm going to end up getting that the average acceleration is 2 meters per second squared. Change in velocity divided by change in time, and that time interval in this case was 2 seconds. I could do an instantaneous acceleration by estimating again. If I want to get if I want to do an instantaneous acceleration, change that to say instantaneous at, so take that off for instantaneous, at t equal 1 second. And I'm going to use delta t is 1/10 of a second. So I'm going to make my time interval pretty small, just 1/10 of a second. Well, that means I need to find my velocity 1/10 of a second later. I know my velocity at 1 second. What's it at 1.1? So at 1.1 second, this came out to be 60.605 meters per second. Notice I'm not rounding anything because I don't want to round in the middle of the problem. I want to round it to 3 digits at the very end. So my acceleration, if I use that as being almost an instant, it's going to be 60.605 minus 60.5. That time interval was 0.1 second. 60, that's going to be, let's see what my math gives me. That's going to be 0.105 meters per second. divided by 0.100 second comes out to be 1.05 meters per second squared. Remember before when we did the average from 1 to 3, it was about 2 meters per second squared. But when we stopped and made it really, really small, we saw that we got a time interval of about, with a time interval of about 0.1, came out really little, much smaller. Okay. Velocity, time graphs. Velocity is going to go over here. And it's possible that the velocity could be positive or it could be negative. I'm not going to look at a negative velocity right now, but the velocity will go here. Time will go here. Suppose we have a velocity graph and it looks something like this. Again, if I were to draw a straight line here connecting those 2 points, that slope would be the vertical change, which is the change in velocity. That run this way would be the change in the time. The slope of this line is the average acceleration. It tells you how much did my velocity change, how long was my time interval. This is a big time interval. If I want to get instantaneous, I want to make that smaller. I could make it a little bit smaller, say from here to here. I'll call that B prime. And you notice that's a better estimate of the instantaneous velocity. Okay, that's going to be better. But if I really want to know instantaneous velocity, I need to make that slope, that time interval, go to 0, which means I'm going to be looking at this tangent line. So the slope of the tangent line in this case gives us instantaneous acceleration. If you have a slope that connects 2 points over a time interval, the slope that connects 2 points is an average acceleration. But again, we can look at slopes on velocity time graphs, and slopes on velocity time graphs tell us accelerations. If it's between a big time interval, it's going to tell us an average acceleration. If it's a tangent line, we made that time interval so small, it's instantaneous, then it tells us an instantaneous acceleration. All right, that concludes the first 3 sections of this chapter. And I'm going to stop right here. I know that's a lot to take in one sitting.